Okay. Also, for those online, if you have any questions during the talks, feel free to put them in the chat and then we'll address them at the very end. Otherwise, you can also raise your hand and we'll call on you. Okay, so first up today, we'll be hearing from Abby Waggoner. So Abby obtained her BS in chemistry from Ball State University, and she's now a 5th year graduate student at the University of Virginia. She uses both chemical and disk models and radio astronomy to understand chemical evolution and protoplanetary disk. In 2017, Abby actually participated in the SAO REU program, where she worked with her current PhD advisor, Elsa Cleves. Abby is also an NSF graduate research fellow, and then today she will be talking to us about observational implications of X-ray flares in chemistry and planet-forming disks. So Abby, if you want to go ahead and share your screen and unmute yourself, we're ready.
Okay, thank you. All right, does everything look good from your end?
This looks great.
All right, excellent. So hello, everyone. Thank you for having me be here. I'm super excited to attend even remotely. But yeah, I'm going to tell you all how an astrochemist snuck into the high energy talks today, because I am indeed an astrochemist. So let's get into it. So when we are considering planet formation, this is probably a similar type of image we've all seen at some point, where molecular clouds collapse to form a protostar surrounded by molecular envelope. Over time, that molecular envelope dissipates, and we form a pre-main sequence star within a class 2 protoplanetary disk. And over time, the disk will form planets, and this is how we form planetary systems. So in order for us to understand the chemical composition of exoplanets, which is super important right now because JWST is observing exoplanet atmospheres, in addition, also understanding what are the chemicals that are available to form life, we have to look back in time to the protoplanetary disk phase and understand what is the chemistry that is occurring within this region, or what are the different physical drivers of chemistry? What is causing chemistry to occur? What is driving reactions? And it turns out within protoplanetary disks, one of the main drivers of chemistry, gas phase chemistry specifically, are X-rays that are emitted by the young central star. So these young pre-main sequence stars, meaning they're not burning hydrogen yet, have large magnetic field loops on their surface, and trapped within those field loops are hot ionized gases that emit X-ray photons. And so those emitted X-ray photons are able to penetrate the disk, and in doing so, they can ionize gas phase molecules such as helium and hydrogen. Now, hydrogen can go on to do all sorts of fun things. For example, it can collide with another H2 molecule, resulting in the fluorescence of a UV photon, or it can abstract a hydrogen from H2 to form H3+. So H3+ is one of the main reactants in gas phase chemistry within these regions. So if we know that X-rays are driving H3+ abundance, then we know X-rays are also driving chemical reactions in the gas phase in general. So this is a pretty commonly accepted model. We use this very commonly in protoplanetary disk models, especially when we're looking at chemical evolution. However, X-rays are not constant in time. In reality, stars regularly undergo flaring events where magnetic reconnection, on the stellar surface can emit high energy photons, such as we're seeing in this movie, which is an extreme ultraviolet light of the sun. And you're actually watching a flare occur on the sun's surface. So this regularly occurs within our sun, but when we're considering a younger version of our own sun, or the pre-main sequence version of our own sun, which we call a T-Tauri star, this is especially true where flares can occur on like a weekly to monthly basis, approximately. And so when we're looking at protoplanetary disk chemistry, the next question is, okay, well, we know these stars are incredibly active and bright in the X-ray regime, how is that impacting the chemistry? Since we know H3 plus, which is one of our main chemical drivers, is dependent on the X-rays. So here I'm going to show a movie where this top plot is a simulated X-ray flare over the course of like 20 days. And you're seeing the relative change in X-ray luminosity compared to the characteristic or non-flaring X-ray luminosity. And this bottom plot is showing our fractional H3 plus abundance with respect to hydrogen in the disk, where the star would actually be where my laser pointer is pointing right now. And we're getting further away from the star and like higher up in the disk. So as the movie plays, you're going to see when the flare occurs, this, as expected, we dramatically increase the amount of H3 plus in the disk. And this is dramatic or has implications for other molecules. So for example, what we have found through our studies is that the most flare sensitive species that we can actually observe within protoplanetary disks is HCO plus, or just protonated carbon monoxide. So this reaction occurs when H3 plus just protonates CO gas, and CO gas is the most abundant gas phase molecule other than hydrogen and helium within protoplanetary disks. So it's very easy for this reaction to occur. Now HCO plus is only temporarily enhanced, as you'll see in this movie, which this movie is actually the same as the last one, only we're looking at HCO plus fractional abundance rather than H3 plus. And as our flare occurs, you'll see the amount of HCO plus around a vertical height ratio of 0.4, so near the disk surface, the amount of HCO plus increases. Now, as you're already seeing, the HCO plus is slowly falling back down in abundance, and that's because this molecule is short-lived, meaning it will snag an electron within the environment and fall back apart to reform carbon monoxide. So this species is a really good flare tracer within protoplanetary disks. And actually, we can observe this occurring, and we have done so within the IM loop protoplanetary disk. Ilse Cleves did so in 2017 when they observed IM loop on 3 different occasions. They looked at H13CO plus, the 3-to-2 transition. And this is a spectrum of that line. So if you're not familiar with radio astronomy, don't worry about it. The takeaway here is that this observation day in blue that was done in May 2015 is like twice as large as the other observation days, meaning that the flux of this species doubled. And in doing so, the continuum remained constant, suggesting that this was a genuine increase in the HCO plus abundance and not artificial. So it wasn't an increase in temperature. And the only way to explain this increase in abundance was through an X-ray flaring event. Additionally, follow-up observations that I led in last year with the SMA, or the submillimeter array, have shown that HCO plus has gone back down to this quiescent state. So this is confirmed that this enhancement of H13CO plus was indeed short-lived. Okay, so we now have one point in evidence in which an X-ray flare can increase chemical abundances in a disk. It's not a lot. Well, you can't even make a line with 1 point. So we decided to turn to the MAPS survey. Some of you might be familiar with MAPS. There are a lot of MAPS peoples at the CFA. But if you're not, it was a very large program through ALMA to observe 5 different disks. In doing so, they observed tons of lines, tons of molecules, and had 20 plus papers published all at once. It was a very beautiful, if you're interested more in MAPS, I have the QR code here, please check it out. But what they did is, the way that MAPS kind of worked is these are our 5 disks. And to create these beautiful images, which again, if you're not familiar with radio astronomy, you might be like, oh, that's just kind of a blob. It's a very beautiful blob, just yeah. So what they did is they actually observed each disk multiple times over the course of a little under a year. So this is the disk HD 163296, which they observed 6 different times between October 2018 and September 2019. And they combined all of these images to produce all of these observations to create a single fabulous image. And this is great, and it did a lot of great science goals. But what I actually did is I took this data and I ripped it apart and I created 6 individual images that were a lot less pretty and a lot more blobby to figure out, is the HCO plus flux constant over the course of these 6 observations? And I did this for each of the disks. So we now have 5 more data points. And we got something that looks like this for each of the disks, where each of these different lines, it might not be very colorblind friendly, so I apologize for that. But basically, you're seeing they're all kind of smashed together in the same location. So this is the disk we just showed you, HD 163296, and you can see nothing really jumps out. So, okay, nothing, we don't really have any variability that we detected. Additionally, when we look at the other 4 disks, we see a similar result. We actually don't see any variability in any of these disks. And you may be wondering just by quickly glancing, and I won't spend too much time on these, like the IM loop disk looks like it has an extremely high jump on one observation day compared to others, but this is artificially introduced due to an error in the flux or variability in the flux calibrator. So this is not real. There's a lot to consider when we're looking for variability and what can introduce it. Additionally, though, we did see in 2 of the disks, so especially this one, you may notice this little peak right here is shifted a teeny tiny little bit from the peaks right here. So this may be one source of variability of HCO plus. But at this time, we can't confirm that because our signal isn't strong enough. And we see something similar in this disk where, again, it's kind of a mess, but our spectral shape seems to shift a little bit. So, okay, we have now between these 5 and the one strong detection that Ilse Cleves did, we have 6 disks, and out of the 6, we have 1 detection. So, okay, we know that flares are driving variability, right? But the question now is, with all of this evidence, can we actually observe HCO plus enhancement due to flaring events? And again, yes, in theory. In practice, we're not quite there yet. So a better question to ask is not, can we observe enhancement due to X-ray flares, but how likely are we to observe enhancement due to an X-ray flare? And so to answer this question, we need to understand stochastic flaring events, and we need to model them, and we need to model them accurately. So to do this, and here is why you all have an astrochemist giving a talk to the high energy group, is because I've done this. And I had to ask the question, okay, well, how can I model X-ray flares and import modeled flares into a chemical disk model? And so to do so, there's going to be a little bit of math here. Sorry about that, everyone. But to do model flares, we need to be able to solve this equation, which is saying the number of flares that occur with over a certain energy range is equal to this power law distribution. And the most important part of this equation is this power law index, or this alpha value. And so this alpha is what we needed to solve. But to get that, we need 2 things. We need to know how frequently do flares occur, and also what is the energy distribution of flares. And that will tell us this how many flares occur over what energy range. And so I know at least a couple people in this audience who are part of this project. But to answer these questions, I turn to the Chandra Orion Ultra Deep Project, or the COOP survey. So COOP actually surveyed the Orion molecular cloud. And they have tons of beautiful work and papers. I recommend checking them out. Getman et al. 2005 is the first one. But in this talk, we're considering Wolk et al. 2005. Where this paper focused specifically on solar mass stars. And they found about 30, approximately solar mass stars. And with over 13 days of continuous observations with Chandra, they were able to extract X-ray flare statistics from this survey. And these are the statistics that I used in my modeling. So the Wolk et al. 2005 paper has data that looks like this. This is an actual X-ray light curve, and they were able to extract and determine how many flares occurred or whether or not flares occurred within the data. So for example, in this light curve, they identified 3 flares. I won't get into their actual methods, but basically they used characterized an elevated state and a rise and the rapid exponential rise and decay to identify flares. And using this data, using this method for all of their 30 stars, they identified that a T-Tauri star undergoes approximately 49 flares per year. Now, this is like an average thing. This is not guaranteed. And they also were able to fit the energy distribution of the flares to this power law index, where this histogram is the real observations and the dotted line here is their best fit. And they found a power law index of negative 1.66. So, okay, now that we have that, we have the how often do flares occur and what is the energy distribution of flares, let's actually model them. All right, so here again is a little bit of math, everyone. Sorry about that. But the way that I've modeled these flares is it's a model that I've named XGen, or X-ray light curve generator, is we take that input energy distribution and the flare frequency, and we combine them to create an equation that determines the probability of a flare occurring or not. The probability of a flare occurring is then used with a random number generator to multiple time steps of a model to determine whether or not a flare actually occurred. At every point in which a flare occurred, we then construct a flare shape based on the total energy of the flare, and using a uniform rise and decay time, and we construct individual flares. We then integrate all of the individual flares over the course of the model time to create a single light curve. So here is a modeled light curve from XGen, where you can see this is about a year. This is a year's worth of flaring, and we have some pretty strong flares here that can increase the luminosity by up to a factor of like 35. So lastly, to determine, okay, is our model accurate? Are we matching predictions? The model also goes through and it identifies observable flares using the similar criteria that the Wolk et al. 2005 paper does. And so the very small micro or nano flares are not considered as a part of our observable flares. And we were able to match that to the Wolk et al. 2005 energy distribution. And we actually found our best fit power law index was negative 1.64. So this is how we were able to fit. We were able to accurately model X-ray flares as observed by the COOP survey. Okay, so we have an X-ray light curve. Sorry, we have an X-ray light curve. And the next step then is to include that into our chemical disk model. And I won't bore you all with the details of how the model works, but effectively, we use a point source model where we run chemistry at each of these individual locations over time. And we also include the X-ray flares. And so the X-ray flares are, everything in the model is held constant except for time and the X-ray ionization rate, which is variable based on the flaring events. If you have more questions about this, please feel free to ask afterwards. But we model chemistry for 500 years at 4-hour time step resolution with a 500-year light curve. And this allows us to look at how the total number of species in the disk change. All right, so what did we see? So we saw this. We saw lots of molecules. Our model includes over 600 species, but I'll only show you one here today, and that's HCl+. So here's our 500-year light curve. And I wanted to show you this because it does look like a complete mess. But each of these are very distinct. So if you remember our actual shorter light curve here, you can see that these are very distinct, but when we look at 500 years, they're all smushed together. And this is reflected when we look at HCO plus and how it's affected. And again, this is very crazy. And the takeaway point here is that HCO plus is very sensitive to individual flaring events. And we were able to use this 500-year light curve to determine what are the statistics associated with flaring events. How often are we how likely are we to see HCO plus enhanced? And using our previously observed data of HCO plus and the MAPS data, we can define a minimum criteria that we require in order to observe enhancement in HCO plus. Otherwise, it will just look like noise. And so if we consider our quote unquote most variable disk, which was AS209, we can see that the integrated line flux is approximately-ish 50% higher on the variable day compared to the non-variable days, meaning that we need to see HCO plus enhanced by a flare by a minimum of 50% or more in order to confidently detect this and not So basically, in order to catch a flare or to catch HCO plus enhanced by a flare, we have several things we need to keep in mind. We need at least a 50% increase in the HCO plus abundance or flux, if we assume a 1-to-1 ratio with the flux and abundance. And because of that, based on our 500-year model of stochastic X-ray flares in HCO plus, there is only a 5.3% chance of observing this enhancement if we observe a disk one time, which also explains why we only saw it in one of our 6 disks. And lastly, if we wanted to confidently detect HCO plus enhancement in one disk, we would have to observe that one disk a minimum of 18 times on distinct observation days, meaning like at least like a week or 2 apart. And so this is really hard to do. This would be a lot of observation time for not guaranteed success. And so in this past year, I've actually joined a collaboration that's being led by Konstantin Getman. And our collaboration is working on coordinated observations to make this happen, to ensure that we catch HCO plus being enhanced by a flare. And this will tell us a great deal about disk ionization as well. It will give us information that we've never learned before about disks and the gas phase ions. So to do this, we actually have accepted Chandra observations to look at the Orion Nebula cluster. And Chandra is going to then trigger observations with several other telescopes, including the VLBA, which is also going to study coronal mass ejections, the Haberle-Eberle telescope, which is going to measure magnetic fields. And lastly, my portion of this project is to use ALMA observations to catch this enhancement of HCO plus in disks and to understand how are flares impacting gas phase chemistry in planet forming regions. Okay, so in conclusion, I know we covered a lot of material here, but our key takeaways are that pre-main sequence solar mass stars, or T-Tauri stars, are X-ray bright and variable. X-ray flares from these stars can increase the abundance of HCO plus and planet-forming disks, but there is a less than 5% chance of observing flare-induced HCO plus enhancement, meaning it's just very hard to do. So we need coordinated observations in order to detect this enhancement. All right, so in conclusion, I just want to say thank you all for letting me be here and give this talk even remotely. And thanks to the organizers for putting this all together. And I know I'm here, like, again, I know I'm virtual, but it's still exciting to be at the CFA again. So yeah, thank you.
Great talk. Thank you, Abby. Do we have any questions from our in-person audience? Okay.
Yeah. Hi, Abby. Nice talk. I had a question about what you considered an X-ray flare, if you were concerned about the peak temperature of the flare, if that mattered, or if it was simply the total energy in the flare that impacts your model. Is she
Understand
frozen?
your question now. Do you mean the temperature is in like,
You know, some flares peak out at about 1.5 keV. Other flares may reach 6 keV.
yes, okay.
Does the temperature of the photon matter, or is it simply a function of energy?
Yes, that's a good question. No, the temperature of the photon we are not including. That is something we've thought about looking and exploring in the future. The problem is if we introduce a time variable temperature, we're introducing another variable into the model. And it's also going to make it much more computationally difficult because already we were at like hundreds of years of computation time just to run this 500-year model. So it's something we want to explore in the future. But yeah, at this time, we don't consider temperature of the photons.
Okay, other questions from our in-person audience here?
I have one more.
Go ahead.
Okay, so the other one I had was, how long does it take the enhancement? You said a matter of quote weeks, but do you understand how long it takes the enhancement to go down and whether it's proportional, what it's proportional to?
Yeah, so it is dependent on the flare strength. So a stronger flare will increase the HCl plus for longer periods of time because it results in a higher increase in the HCl plus enhancement, or in the HCl plus peak. But in general, we find that it's about 1 to 2 weeks. I don't think I included this figure in my backup slides. I did. Okay. So this is the HCl plus column density, which is in a disk over time. And so the important thing here is like, you can see after about 10 days after the flare, we still see enhancement in this like green line, but by the end of like 20 days, so like 2 or 3 weeks later, the HCl plus is no longer enhanced effectively at all. I think that answered your question. So.
That's excellent, thank you.
All right, any other questions from in-person? Okay, let me check our online. If there's any questions? Don't see any hands raised. All right, well, with that, I think that's all the questions we have for you, Abby. Thanks again for that great talk. All right, so next up today, we'll be hearing from Tim Cunningham. So Tim received his MS at King's College London and his PhD at the University of Warwick. He's currently a postdoctoral research fellow in the White Dwarf Research Group within astronomy and astrophysics at the University of Warwick, working with Pierre-Emmanuel Tremblay. His research primarily focuses on understanding the nature of convection, in particular convective overshoot in white dwarf atmospheres using CO5 gold, which is a 3D radiation hydrodynamics code. And today he'll be talking to us about white dwarfs as probes of convective overshoot and evolved exoplanetary systems. So with that, Tim, go ahead and take it away.
Great, thank you very much, Amy. Yeah, so I'm a postdoc at the University of Warwick, and it's firstly thanks to the organizers for inviting me to talk to you today. It's very exciting to be here. It's I assume it was designed this way, but it's nice following Abigail's talk where we've been seeing X-rays as probes of protoplanetary disks. The main focus of my talk today is going to be how we can use X-rays to probe evolved exoplanetary systems once they've reached the end of their life. So that's a little teaser of what I'm going to cover. The work that I'll present here has benefited from collaborations with the people shown on the screen here. So to kick off, I'm going to try and touch on these things and how we can use white dwarfs to probe the following things: exoplanetary compositions, hydrogen burning during the asymptotic giant branch, and accretion physics. Just a quick introduction as to what a white dwarf is. A white dwarf is the stellar remnant left behind at the end of stellar evolution for stars that have an initial mass of less than 8 solar masses. We can think of it as something like the mass of the sun and the size of the Earth. This leads to high surface gravities and fairly rapid elemental sedimentation. So the canonical structure of a white dwarf is something like this: a carbon-oxygen core with a helium shell on top and a hydrogen shell on top of that. In about 20% of cases, white dwarfs don't have this outer hydrogen shell, instead just having a helium shell. And for a long time, we had these canonical numbers that 10 to the -4 of the star comprised hydrogen. Some of the work, which I might not have time to get to today, but if I do, we've been able to update this number. We now know that there's really a continuous distribution of primordial hydrogen content left in white dwarfs. And this is something I've been working on to constrain hydrogen burning during stellar evolution. So white dwarfs should have a pristine either hydrogen or helium atmosphere. So in spectroscopy, we expect to see just hydrogen or helium absorption features. Over 100 years ago now, back in 1917, Van Manen 2 was the spectrum shown in the middle panel here, showed evidence of heavy elements in the atmosphere. At the time, it wasn't known this was a white dwarf, but in hindsight, it turns out this was the very first evidence of exoplanets. A few decades later, it was realized that this was in fact a white dwarf. And I'm showing the spectrum here. We've got calcium H and K lines, magnesium and iron absorption features. So this was the first evidence of exoplanetary material in the atmosphere of white dwarfs. Since then, we've now had 23 unique metals detected in the photosphere of white dwarfs, including those necessary for formation of crust material on planets, as well as things required for life as we know it. So white dwarfs are really unique tools for probing the composition of exoplanets. We now have a catalog of 360,000 high confidence white dwarf candidates, and we're in the process of a very long spectroscopic follow-up to confirm all of those. Typically we expect a quarter to a half of white dwarfs to have heavy metals in their atmosphere, and the frequency with which white dwarfs exhibit these metal absorption features implies that this material must be being accreted after the formation of the white dwarf. If these metals were primordial, they would sink on very short timescales towards the core. So how do these metals find their way into the atmosphere of a white dwarf? From exoplanet studies, we know that something like a third of stars have an exoplanet associated. It's likely that lots of these exoplanetary systems, the planetary bodies, are likely to survive the stellar evolution, and so there might be lots of planetary bodies still gravitationally associated with the white dwarf. If this material reaches the Roche radius of the white dwarf, which is about 100 times the white dwarf radius, then it will be tidally disrupted. And there's lots of observational and theoretical evidence that planetary bodies will be scattered by themselves towards the center of gravitational potential where the white dwarf sits. And so when they reach the Roche radius here, they're likely to tidally disrupt and form a debris disk. And we have evidence of this in many forms now. So we have infrared excess, which was the first hint of some circumstellar material. We also have gaseous emission detected in tens of systems now. We also have actual transits of planetesimals and planet candidates. So we have strong indirect evidence of circumstellar material. Well, we have strong evidence of circumstellar material around white dwarfs. And the key piece of evidence for the accretion of planetary debris is, as I've mentioned before, the atmospheric pollution. So the absorption features from metals in the optical and UV spectroscopy. We can use the photospheric metal absorption features to derive accretion rates, and that's from the accretion rates, and to derive accretion rates, as well as the composition of the parent body. But to do both of those things, we need detailed white dwarf atmospheric models. So if we combine our metal abundance in the atmosphere with a settling time from white dwarf atmospheric models, we can get an accretion rate for each element and find a total accretion rate. And this can be a useful number if you want to probe numbers such as the lifetime of debris disks around white dwarfs and the actual mass of metal that has been accreted. But this diffusion timescale is very sensitive to what physics you include in your atmospheric models. As Amy mentioned in the introduction, I spent a lot of my PhD working on convection in white dwarf atmospheres. And it turns out it's very important to get convection right. As white dwarfs cool, they develop a very superficial surface convection zone. This is massively enhanced here for visual reasons, but typically the white dwarf convection zone will start at about 10 to the minus 16 of the stellar mass, and that will be confined to the very surface layer. So it's a very small part of the star, but actually defining the true extent of this convection zone is very important for setting both the mass that the metals are mixed into, as well as the diffusion timescale. And modeling convection has been done for almost a century now using mixing length theory. And one of the key things mixing length theory omits is convective overshoot. And studying this in detail was a key part of my PhD work. To study convective overshoots, I used the 3D radiation hydrodynamics code COBOLD. Convective overshoot, just for those that are not familiar with the term, describes the additional mixing that happens outside of the unstable layers defined by the Schwarzschild criterion for convective instability. So mixing length theory does a good job of replicating convective velocities, and it does do a good job of saying where convective instabilities arise. But what it fails to account for is the fact that material accelerated near the boundary still has sufficient momentum to penetrate the formerly stable layers. This is why we need multi-dimensional simulations. Just to give you an example of our simulations, this is looking down at the surface of one of our simulation boxes, and this is a snapshot of the emergent intensity. On the left here is observation of the sun. So we have qualitatively, you can see we have this granular convective behavior here. But I'll just point out that the length scales here are 3 orders of magnitude different. So the white dwarf convection zone is very small, and these characteristic granule sizes are on the order of 1 kilometer. It's not feasible to simulate the entire star, so we have to use box in a star setup using periodic boundary conditions on the side. I use the code COBOLD, and this solves the equations of mass, momentum, and energy conservation in this periodic plane parallel approximation. Most of the time is spent solving radiative transfer matrix in this energy conservation equation. And for us, this is extremely important because we cover optical depths from 10 to the 4 down to 10 to the minus 10. And it's in this really optically thin regime that the radiative transfer becomes most important for accurately modeling the hydrodynamic flows. Yeah, so this is the box in the star setup that we use. So we embed a simulation box inside an atmosphere with equation of state, and opacity is appropriate for the atmosphere. Here I'm showing 6 movies. They might not play all that well over Zoom, so apologies if they're a bit jumpy. But blue shows you where convective flows are happening. So the length and it shows you the magnitude and direction of the local hydrodynamic flows. These are vertical slices through a 3D simulation box embedded in the atmosphere. So the surface of the star, let's say, is up here, and down here is towards the core. The z-axis, or the y-axis, is normalized at the lower Schwarzschild boundary. So the key takeaway here is that in mixing length theory, mixing only occurs due to convection for positive values of z. I'm not sure how well the video is played for you, but the point here is that with these multidimensional simulations, we find that there's significant mixing happening at these negative z values. So using multidimensional simulations, we find that the convection zone is actually capable of mixing a significantly larger amount of material than the mixing length theory would predict. So you can see this is in kilometers. So the mixing length theory, we'd have, say here at 13,000 Kelvin, 13,500 Kelvin, we've got convection zone over less than a kilometer, but actually we're mixing kilometers worth of material underneath. And this is, I've shown this for 3 white dwarf temperatures, 13.5, 13,000 and 12,000 Kelvin. And this is in some sense chronological. So the white dwarf is cooling towards the right. So from this, we can derive diffusion coefficients due to convective overshoot. So this green stuff here is a passive scalar that's moved around, and I use this to derive local diffusion coefficients due to convective overshoot. And this is the key quantity that allows us to actually define effectively how big is the overshoot region. And so this is what I've done here on the left. So this is the mixed mass for 2 prescriptions, one with in blue and one without overshoot in red. So without overshoot, when convection, when the white dwarf cools and the convection zone first forms, the size of the convection zone is about 10 to the minus 17 of the star. With overshoot, that increases to 10 to the minus 16. So we have an order of magnitude increase there in the size of the mixed region. As the white dwarf cools, these 2 models diverge to a maximum of 2.5 orders of magnitude increase in the mixed mass here at 13,000 Kelvin. I'll just point out that the hydrogen opacity bump occurs around 12,000 Kelvin. And this, I didn't mention before, but this convection is driven by the partial ionization of hydrogen. So this is some explanation for why the divergence is so great here. This increasing the size of the convection zone also increases the diffusion timescales. That's what I'm showing here on the right. And so here you've got the difference between the mixing length theory with the dots and the full overshoot with 3D hydro in the solid lines. So here we get a 2 order of magnitude increase in the diffusion timescales. And these also affect the relative diffusion timescales. And this is what's really important for exoplanetary compositions, that if you're trying to work backwards from a white dwarf photospheric abundance back to a parent body composition, you need to know your relative diffusion timescales. So including the appropriate physics in the atmosphere is important for this, using these as a probe of exoplanetary compositions. And if you combine those 2 things together, we end up with a prediction that the accretion rate with convective overshoot increases by about a factor 5. Another piece of work I'd like to highlight from one of your colleagues there at CFA, Evan Bauer, is the inclusion of thermohaline mixing into white dwarf atmospheres. This predicted to increase in the warmer white dwarfs the accretion rate by around 3 orders of magnitude. So you can compare here the white and the blue points. So we've got some open questions about what physics needs to be included in the atmosphere and quite different predictions about accretion rates and diffusion timescales. I also want to highlight another perhaps observational conundrum in that I've already mentioned infrared excess as a probe of circumstellar material. There were two papers a couple of years ago by Andrew Swan and Laura Rogers that Andrew found that there's certainly evidence of infrared variability in debris disks, whilst Laura Rogers at shorter wavelengths found that there was no evidence for variability. So we have some evidence that these debris disks are varying in their infrared flux, but we don't actually know whether that will imply any change in their accretion rate. So we have different physics in the atmosphere, and we have this question of is the accretion rate onto white dwarfs variable? So I've shown this plot before, and I just want to point out that all of the evidence that we've had over the last few decades of metal pollution and the accretion of planetary debris onto white dwarfs has been indirect, very strong, but indirect evidence that ongoing accretion is occurring. We've had a sort of Occam's razor scenario where we have circumstellar material and we have metals in the photosphere. So we know that this material is moving from the debris disk to the white dwarf surface, but we've had to assume that this accretion is ongoing. I saw the first direct evidence of ongoing accretion in the form of X-rays. As I probably don't have to tell anyone in the audience, X-rays have been ubiquitously used to study accretion processes, but normally at much higher accretion rates than those that we see in white dwarfs. I should have pointed out before that typical accretion rates are sort of on the order of 10 to the 9 grams per second. So compared to a cataclysmic variable, for instance, we're accretion rates like 4 or 8 orders of magnitude lower. And that's one of the reasons this had never been detected before. If we were able to use X-rays and get an X-ray detection, then it would provide an independent test of atmospheric models and potentially allow us to probe this question of variability and accretion rates. I targeted G29-38. This is the prototype for all metal polluted white dwarfs. It was the first one to have an infrared excess detected. At the time, it wasn't known if that was due to a substellar companion or a circumstellar debris disk. We now know that it is a debris disk, and in fact, this is the infrared spectrum of G29-38. So the reason that we get an independent constraint on our atmospheric models is this. In the traditional sense, well, I say traditional sense, but when we infer an accretion rate from spectroscopy, we couple an observed metal abundance with a convection zone mass and a diffusion timescale. But these two quantities here are both model dependent. So these require atmospheric models of your white dwarf. A detection of X-rays provides an independent constraint, because if we can measure an X-ray luminosity, then we can approximate the accretion. Oops, I didn't mean to do that. We can approximate the accretion rate by converting the gravitational potential of the infalling material into this X-ray luminosity. So to derive an X-ray luminosity, X-ray accretion rate, we just need to measure an X-ray luminosity, and we need to know the white dwarf radius and mass. These two quantities are much more reliably constrained from either spectroscopy or photometry. And so it's in this sense that working out this mx dot that we can provide an independent constraint on these two things. So we targeted G29-38 with Chandra back in September 2020. We had a 32-hour observation of our target. In that time, we detected 5 counts. That's what I'm showing here on the left. Those 5 counts were sufficient to confirm our target to a significance of 4.5 to 5.9 sigma. This was largely due to the sensitivity of Chandra's ACIS-S, where the expected background in that exposure time was 0.1 photons. So here I'm showing here the 2, 4, 5 counts detected within 1 arc second of the expected position of our target. In the middle, I'm showing the same counts image, but convolved with the PSF of ACIS. And on the right, I'm showing an optical image taken 7 years before our observation from the Pan-STARRS I-band. What you will notice is that there's a much brighter source nearby. This object was targeted previously with XMM, but the angular resolution of XMM is on the order of 10 arc seconds, which is the distance between these two things. So our target was completely lost, completely swamped by the brightness of this object. So it was really the angular resolution of Chandra that we needed to make this detection. All of the 5 photons we detected are very soft in energy, 1.3 kilo electron volts or less. So that's what I'm showing here, our X-ray spectrum of our 5 photons. This gives us the softness of our detected photons gives us a very good constraint on how hard the X-ray emitting spectrum is. Here I'm showing the ACIS passband, and you'll see that most of the sensitivity is at harder energies than what we've detected. So we're pretty confident we have a very soft source of X-rays here. From our 5 photons, we can fit spectral models. So we fit 6 different, a combination of 2 plasma models, an isothermal model and a cooling flow model with 3 different abundance profiles. And this allows us to constrain the plasma temperature. And from that, we can derive an X-ray flux. The temperature that we've measured, we think, is the first confirmation of this bombardment solution that was proposed by Kuipers and Pringle back in 1982. Most accreting objects that are measured in X-rays are forming a strong standoff shock as the infalling material approaches the stellar surface. In the bombardment solution, at low accretion rates, the infalling material is behaving less like a fluid, so that no shock is formed above the surface, but instead the atoms are directly impacting the atmosphere and mediating their energy into the atmosphere over one mean free path. And so in this model, they predict a much lower plasma temperature of 0.6 kilo electron volts, which is in line with what we've measured here. We can also derive our X-ray accretion rates, and that's what I'm showing here in blue. So the blue band is our is the 1 sigma confidence interval on our X-ray accretion rate for the 2 plasma models and 2 sets of abundances. And then in green and pink, I'm showing the predicted accretion rate based on the spectroscopic observations of the metals in the atmosphere. So the main conclusion here is that the measured X-ray accretion rate agrees very well with the inferred accretion rate from spectroscopy. And this is a very exciting result because it gives great confidence in the spectroscopic technique, because this is an independently measured accretion rate based on a different wavelength and different physics. So this is a nice confirmation of existing techniques using spectroscopy to infer an accretion rate. But we do find that the overshoot models with enhanced mixing are somewhat preferred over those models without overshoot. But really, this blue band, this measured X-ray accretion rate, should be considered as a lower limit on the accretion rate. This is because we've probably detected the high energy tail of a emission spectrum, and so the main uncertainty is how much of that X-ray luminosity is being carried at other wavelengths. We can pretty much rule out any flux in the radio, because there's an upper limit of 1.5 kilogauss on the magnetic field of this object. So we don't believe, we predict negligible cyclotron emission cooling. But the greater sources of uncertainty is how much flux is carried in the extreme ultraviolet. So to try and put a handle on that, we integrated our best fit plasma model down to the Lyman limit, and that's what I'm showing here. So here you've got the 68 and 90% confidence intervals on the accretion rate. And these really asymmetric error bars are due to the fact that the detection gives us a very nice lower limit on the accretion rate. The upper limit is much more difficult to pin down. The good news is that I have follow-up observations on this object, and I'm hoping also with Chandra. So we're confident we're going to be able to improve the uncertainties at the higher end here. So in conclusion, our recent observation confirms metal-polluted white dwarfs as a new class of soft X-ray source. The measured X-ray flux provides the first independent constraints on the accretion rates of these objects. Our accretion rate is consistent with the spectroscopically inferred accretion rates. And our X-ray accretion rate appears to favor models with enhanced mixing, such as convective overshoots or thermohaline mixing. So we will certainly be able to improve this with future observations. And we will also be able to use our future observations to try to constrain the variability of accretion rates at this particular object. So with that, I will thank you for listening and happily take any questions.
Thanks for that great talk, Tim. We'll first take questions from our in-person audience here.
Thank you very much, Tim. Very nice talk. I have a source, I don't know if you're familiar with it, QS Virginis, that has a difference of a factor of 1,000 in the X-ray versus the white dwarf settling time accretion rates. I was hoping that your that your models would be getting larger than a factor of 5 difference. Do you hold out any hope that we can reconcile those two accretion rates?
Interesting. Yeah, I'm not familiar with the system. Did you say QS Virginis?
Yes. Yeah. Ask Boris about it. He knows about it.
Okay. And this is a metal polluted white dwarf or a CV?
Yeah. It was a. It's a. It was thought to be a pre-CV, but it is accreting at a very low rate that's lower than any normal CV rate. So 10 to the minus 12 solar masses a year or something.
Right. But in this case, it's accreting hydrogen, right?
It's accreting from a or yeah.
Yeah. So my models, I don't think, yeah, these models won't provide much insight into cataclysmic variables. So here we're really talking about the accretion of rocky debris, and I don't think, yeah. So I don't think that, yeah, we're in quite a different regime, I think, than a white dwarf accreting from a main sequence companion.
Maybe we can talk after.
Sorry. Yeah, that would be good. Yeah.
I see John Raymond has a hand raised. Go ahead, John.
Hi. I was wondering if I remember correctly from all those years ago, the Kuipers and Pringle solution assumed radial accretion. And it seems like if you have a debris disk raining dust in, it's basically in Keplerian orbits working its way in, so that you'd have something more akin to meteorites than the Kuipers and Pringle assumption.
Yeah, they do assume radial accretion. At the moment, we don't really have a good constraint on how material is moving from the disk to the white dwarf surface. So that's something that I'm very interested in improving models of, because you're right, the material in the disk we know to be following Keplerian orbits. That's clearly, I showed a plot with like gaseous emission in spectra, so that double peaked gaseous emission is from the Keplerian orbits of this gaseous material. But yeah, the bit between where the debris disk is and the white dwarf surface, the geometry of how that material is flowing from one to the other is very poorly constrained or completely unconstrained right now. So yeah, I think there's certainly more work to be done there. But yeah, that's a good point.
I would imagine that it would depend a lot on the size of the particle because it sort of starts off with Keplerian orbits, and then there's drag, both due to radiation and the particles that it encounters. So
Yeah.
it begins to spiral in.
Yeah, there are. Yeah, I think it will certainly start to spiral in, and probably by the time the material hits the surface, we're probably looking at fully ionized atoms just bombarding the surface. But yeah, in terms of the velocity profile of that material, that is a bit of an open question, I would say. That is something I have a project which is jointly modeling X-ray and UV observations to try and constrain the accretion physics a bit better. But yeah, that's a good point. Thank you for raising that.
Okay, I think we're actually out of time. So we will thank our speakers again. I think they still have some slots available. Otherwise, feel free to reach out to them by email. So we'll see you all next week. Thank you.